I'm happy to talk a little bit about the Advanced Carbon Council and who we are. The Advanced Carbons Council is a global trade association representing the engineered carbon sector. We originally were formed as the Graphene Council in 2013, and we've expanded to cover all engineered carbons, including macro forms like carbon fiber, biochar, and other engineered carbons like synthetic graphite. Graphene remains a main focus of our activity and will be the topic for today's discussion. The Advanced Carbons Council is pleased to host today's webinar presented by NanoIntegris Ray Moore using graphene in battery applications. And with that brief introduction, I'm really happy to hand over to Jefford Humes, who represents NanoIntegris Ray Moore. He's joining us from Canada today. So Jefford, walk us through your presentation and the materials you have in this interesting application, and I'll join you back for Q&A at the end of your session. Thank you very much.
Thank you very much, Terrence, for that introduction. Good morning, everyone, or good day, or evening, depending on where you are. My name is Jefford Humes. I'm the Director of Business Development at NanoIntegris and Ray Moore. And today, the topic of discussion is not all graphene is created equal, the role of quality and structure in battery applications. As many of us know, graphene is within what I will call one of carbon's wonder materials. Ever since the discovery of buckyballs by Richard Smalley in 1985, many new carbon-based materials have come onto the scene, such as single-wall carbon nanotubes, multi-wall carbon nanotubes, nanohorns, and graphite, of which graphene is a subset. Graphene is subdivided into few-layer graphene, multi-layer graphene, and monolayer graphene. But what allows these materials to be called wonder materials are because of the properties that they exhibit. For instance, the ideal monolayer of graphene has been found to have a strength 200 times that of steel and a conductivity 10 times that of copper, a current capacity 1,000 times that of copper, all while absorbing only 2.3% of its incumbent light. Focusing on graphene itself, it's also been shown to be involved in numerous electronic applications and show its benefits there, such as in field effect transistors, transparent conductive electrodes, flexible and wearable electronics. The list goes on. But today, I would like to focus upon the use of graphene within battery applications. Now, of course, batteries, there's numerous types of batteries in this world. We'll narrow it down and say, okay, there's maybe 10 to 15 main commonly used types of batteries. The issue is that one type of graphene cannot satisfy the demands of the world's numerous different types of batteries. But what's great is that graphene itself, though, is able to provide benefits to at least 7 types that I've listed here, such as lithium-ion batteries, lithium-sulfur batteries, sodium-ion batteries, potassium-ion batteries, zinc-ion, aluminum-ion, and one of the latest incumbents, solid-state batteries. But graphene itself is defined by the technique that's used to produce it. And there are essentially 2 different ways of producing graphene. There's a top-down approach and there's a bottom-up approach. For our purposes today, I'll deal with about 5 different types of top-down production techniques for creating graphene. Mechanical exfoliation, liquid phase exfoliation, electrochemical exfoliation, chemical oxidation reduction, talking about the production of graphene oxide through primarily the Hummer's method, and ball milling. For the bottom-up approach, there's also 5 that I'll put my focus on today. Production by chemical vapor deposition, plasma-enhanced chemical vapor deposition, epitaxial growth on silicon carbide, molecular beam epitaxy, and organic synthesis, or AKA a molecular assembly approach. So these are essentially the 10 ways in which graphene, I would say, is most efficiently produced. But I hope that you're wondering, well, how does Raymore go about producing its graphene? So Raymore uses its inductively coupled thermal plasma reactor in order to produce the graphene on site here in Canada. It's a synthetic production technique in a single step, but even so, it is considered a continuous production technique. And because of this, it's a very high yield and very highly scalable technique. So we're already at multi-ton capacity as we speak, which we're very proud to state. The other thing that we're very proud of is that it's an eco-friendly and environmentally friendly synthetic technique. So it's produced by the hydroelectricity of Quebec, also using inert gas, and it does not use any catalyst. And along with this, we neither utilize or produce carbon monoxide or carbon dioxide in the generation of the material. We are an ISO 9001 2015 certified facility, and all of our synthetic techniques are backed by slew of domestic and international patents. With that said, if you'd allow me to digress a little bit, I'll give you a bit of an introduction about who we are as a company. So we are a high-tech company focused on the production of advanced nanomaterials. We're a manufacturer of high-value additives and actives such as the fuel-layer graphene that we're going to deal with in more detail today, and a full spectrum of single-wall carbon nanotubes ranging in purity from 70 to 99.9995% purity. We're a privately owned Canadian company operating out of the northwest suburb of Montreal. And we've invested heavily in nanomaterial R&D for the past 15 years with a team of international and dedicated chemists and engineers. In terms of our leadership, we're proud to be led by Serge Goulet, who is the former CEO of Optimum Reassurance. NanoIntegris was founded by Professor Mark Hersom, who's the chair of the Materials Science and Engineering Department at Northwestern University. The chairman of our board and former CEO is Jacques Millette, who was also the former president, who was also the former chief director of Quebecor. Joining me later will be our quality control manager, Natasha Shogi, during the question and answer portion of this talk. So now I'll tell you a little bit about things on the NanoIntegris side. Basically, we're two companies in one, NanoIntegris and Raymore. On the NanoIntegris side, it's known for, or we are known for, the nanotube purification. So we can take nanotubes from various types of production sources, such as chemical vapor deposition, arc discharge, and laser ablation. We remove the carbonaceous impurities in the metal catalyst, and then form a highly pure single wall carbon nanotube solution that can then have its properties enriched to be either completely metallic in nature or semiconducting in nature, or having semiconducting properties. And because of those semiconducting properties, the material can be used in many different types of applications, such as very large scale integration, integrated circuits, gas detectors, display backplanes, radio frequency technology, printed TFTs, biochemical detection, and wearable sensors, all with a focus on being flexible, transparent, and having low power consumption. Though we're a relatively small company, we're very proud that we have an extensive marketing and sales reach that has reached many prominent institutions over the years, with major markets within North America, Europe, and Asia. And along with this, there's been many proof of principle applications using our nanomaterials, with over 2,100 publications over the last few years. All right, now back to our regularly scheduled broadcast, which is graphene. So the graphene that's produced in our inductively coupled plasma reactor is very unique. Now, typically, graphene has a type of alignment, either within its layers, between its layers, either AB, AA, or ABC alignment. What makes the graphene that we produce unique is that it has what's called a turbostratic morphology. What that means is that it leads to weakened interlayer forces, which might seem like a bad thing, but due to this layer misalignment, it allows for easier separation of our graphene sheets. The smaller graphene aggregates that are produced are make this material easier to disperse, and the reduced tendency to reaggregate leads to more stable dispersions. One of the things that I will be transparent and kind of warn about is that it is best to use our material in its raw form, but functional groups can be added. But we have found that with adding functional groups does convert the SBT to SB does cause SBT to SB3 hybridization, which might reduce electrical conductivity and may also compromise thermal conductivity by creating defects in the lattice structure. But still, this has still been done effectively. I just wanted to be transparent and talk about that property. What is great, though, about the technique that's used to produce this nanotubes is that we can produce it from numerous types of hydrocarbon feedstocks. We can use any from propane, ethane can be used, or butane. But we've found that the highest quality material with the highest crystallinity, as can be seen from this Raman signature and spectrum here, is using methane or methanol to produce our Purewave graphene, with methane being the preferred feedstock for our material. But maybe the one of the ways, in terms of the production technique, the material is produced as comes straight out of the reactor, the form of a powder, with few layers, 1 to 7, making this a few layer material, with a very good G to D and 2D to G ratios, as you can see once again from the Raman spectra. It has very low metals, less than 10 parts per million. And when it comes to polyaromatic hydrocarbons, each batch is produced either with no or very little parts per million PAHs produced. The material is thermally stable, as can be seen from our thermogravimetric analysis, with a stability at or even above 600 degrees Celsius. Now, the lateral flake size is a bit on the smaller end compared to some other techniques, between 100 to 200 nanometers, but the bulk density is very good, 28 kilograms per cubic meter, with a BET surface area up to 450 meters squared per gram. Apart from just producing the material as a powder, we're also very proud that we're able to disperse our powders into an aqueous dispersion at very good loadings. We're able to obtain graphene loadings of 6 to 10 weight percent. With very good particle sizes, 238 nanometers, and do so with very reasonable viscosities, less than 150 centipoise. And you would think that maybe with the thickness of such a solution, it would lead to great instability, but we've found that the stability indexes are very good and that the shelf life can be anywhere from 6 months to 1 year or even more with our testing and those done with partners as well. But one of the focus of this talk today is to tell you about the different types of graphene and their applications in battery settings. As I said earlier, there's many different types of graphenes that are produced and that have benefits to different battery types. For instance, in chemical vapor deposition batteries, it's been found to be very effective in solid state lithium batteries and thin film micro batteries. For graphene produced by mechanical exfoliation, it's been beneficial to research grade lithium ion batteries and lithium metal batteries. For graphene produced by liquid phase exfoliation, it's found great usage within lithium-ion batteries, silicon anode composites, and in cathode additives. And graphene produced by graphene oxide has found great usage within lithium sulfur batteries and sodium ion batteries. And lastly, plasma enhanced graphene has been quite effective within supercapacitors and lithium ion capacitors. And once again, I hope that you're asking, well, where does Raymore fit within its battery applications? I'm very proud to say that our Purewave graphene addresses the biggest issue with the usage of silicon within lithium-ion batteries. So, as many here may know, silicon particles will expand and contract on charge and discharge, eventually leading to the destruction of the particles after many cycles. This will decrease battery performance and life. And this expansion can be as large as 400% with certain types of cycling. With our with our Purewave graphene and its turbostratic morphology, what has been found is that our graphene is actually able to wrap the silicon particles to reduce this expansion substantially. It reduces, therefore, graphite usage and dead weight in the battery, increasing cycle life, decreasing overheating, and increasing capacity, as can be seen within this research that was done at Northwestern University. We're very proud to be partnered with a battery materials company that actually uses our graphene within their silicon-based batteries. And with that, I've seen many wonderful properties, such as benefits to energy density with a 30% improvement versus graphite, and a concomitant EV range increase by the same margin. In the 18650 cells that use our graphene, there's been a 52% increase over, for instance, example battery seen here, with a performance of 800 watt hours per liter. The portable devices have had up to 15% longer runtime, or in this case, 8 additional usage hours, with power cells up to 15, showing 15%, 50% more playback time and 50% more maximum power runtime. In terms of longevity and durability, the cycle life has also been great, over 1,000 cycles to 80% rated capacity under EFI usage conditions. And when it comes to calendar life, over 90% of the original capacity is retained after 3 months at a current 60 times its rated capacity at 100% state of charge. As stated earlier, the use of our graphene has reduced swelling significantly, a 75% reduction in swelling versus traditional silicon, making these types of batteries ideal for first-person view, drones, radio-controlled vehicles, and any type of high-drain electronics in general. Cost and compatibility, of course, is always one of the big concerns. But the silicon anode material that uses our graphene achieves cost parity with synthetic graphite on a per energy basis, and is found to be compatible with various cathode chemistries, cell designs, including solid state cells. Additional usages, battery usages for our graphene can be found within lithium iron phosphate in the cathodes to increase weight energy density and reduce agglomeration of the LFP particles. When it comes to nickel manganese cobalt oxide, graphene could potentially be used in the anode or the cathode to enhance conductivity, improve structural stability, increase capacity, and as well as increasing charge speeds so that the NMC batteries could reach near LFP levels. When it comes to lithium cobalt oxides, our graphene also could be potentially used there as well to lead to higher energy density, faster charging, and improved cycle life. So yes, graphene is indeed one of batteries' wonder materials. And we seeing the growing market. The global battery market is set to burgeon all the way to $483 billion dollars. And we're very proud that our graphene could be used and is being used within batteries that are set to comprise 64 to 75% of that growing market. Thank you for your time, and we'll now take a few minutes of questions. I'll be joined by my colleague Natasha Shogi.
Excellent. Jafar, thank you so much for that. It's a brief presentation, but quite comprehensive, really interesting, and appreciate that. Natasha, did you want to make any comments at first, or do we just go right to the questions for you guys?
I just wanted to say hi everyone, and no, Jefford explained pretty well, and we can start the QA.
Okay, excellent. And then Jeffrey, if you want to stop sharing your slides, we'll just go to a discussion
Oh,
mode,
okay.
and then we'll get into the questions. I did have a first question. You mentioned a comparison in price, and we won't go into actual prices on this webinar. It's not appropriate in a public forum, but we will. You mentioned about compatibility with synthetic graphite, and I just wonder, because of the other performance characteristics of your material, how do you compare with synthetic graphite if that's the closest analog material? How would you describe that comparison?
Right. Yeah. Well, I'll also allow Natasha to answer this as well. But what is great with what's great with our material versus synthetic graphite is that it's been found to not only lead to, as I said, this benefit, for instance, with the silicone wrapping, but a substantial increase in the conductivity. So you'll have, increased electronic properties as compared to graphite. Of course, the price point will be higher, but we believe that the performance benefits definitely outweigh the increase in pricing. Go
And
ahead.
also, I want to add that our graphene has a limited number of the layer. And as you know, that the idle graphene, that's a monolayer, has a really amazing characteristic. And I don't think so that with the other technique we could have less than 5 layer graphene, which increase the conductivity and is not comparable with the synthetic graphite. Because the graphite has a multi-layer, and also our graphene is a turbostatic. It means that the interaction between the layer is less. It means we can have, after the dispersion, we can have a monolayer and its effect on the conductivity as well.
Okay. We did get one of the early questions, and I know we have quite a few coming in, and that's great. So keep the questions coming. We'll get to as many as we can. One of the early questions was about the front part of your presentation about the carbon nanotube. So maybe we'll address
Yeah,
that quickly.
sure.
It just asked about the question is, what is the scale of purification of the nanotubes? And I'm not quite sure exactly what that question means, but I guess it's the level of purity of the carbon nanotubes. Is that
No, I believe that they're just wondering about the level of scale. Ma with many nanotube companies that produce at our level of purity, everything was produced in milligram quantities, nanogram quantities. So I think they're just wondering, do we have the potential to scale up to address market needs? And yes, we do. We've been a part of, numerous wonderful grants, NGen, DARPA projects, and so we've established that in the scalability of our process, where we have the capacity to do it as needed to meet market demand. That's what I can say at this time.
And I guess it's important to point out you referred to single wall carbon nanotubes as well.
Right. Yes. Yeah, that's our primary focus. We really, this company was established, for the purification and usage of single wall carbon nanotubes and its enrichment, either as a metallic material or a semiconducting material. We are not producers of multi-wall nanotubes. That's not our focus. We've found so many numerous applications that use single wall nanotubes, and that's been the market that we've been looking to address.
I
Excellent.
just wanted to add other things, terms.
Of course.
Yeah, the beauty of the nano integrates and Raymore is the separation of the carbon nanotube. We have a metallic carbon nanotube and also semiconducting carbon nanotube. Semiconducting carbon nanotube is really amazing for the electronic industry, and we have a 100% of semiconducting carbon nanotube, which is our strength also.
Excellent. Well, just to point out, single wall carbon nanotube, there are not that many producers. The vast majority, and of course by volume, is multi-wall carbon nanotube, and the materials do behave differently. But I want to point that out. And also, a little selfishly, just it underscores why we changed to Advanced Carbons Council is we have companies like yourself that are making not just graphene, but other morphologies of engineered carbon. So that kind of proves the logic of us pulling all that together. So if we get back to the main topic here, we're talking about the graphene production you have in battery applications. We do have a question asking about the turbostratic morphology, which is exactly the morphology you get when you have this gaseous precursor material and then you have this cracking of the methane. You get this turbostratic graphene, which we've seen and tested ourselves as the ACC a number of times. Can it effectively be dispersed in a polymer melt mixture? So it'd be like a thermoplastic. That's not the battery topic, but still, it's a question from the audience. What about thermoplastic integration of your material? Have you done some application development in that area?
Okay, we haven't directly done the development there, but we were actually a part of an international partnership that was looking to use our graphene in just that application, thermoplastic, biodegradable plastic using our graphene. So we know that theoretically, it works, it can work, and with our few layer graphene. There's been some proof of principle to show, that is one of the potential applications. But we didn't, move forward with doing that work after all, full transparency. But it is an application that, we've touched on in the past.
No. Well, I can just confirm graphene of many different grades in plastics of many different grades, basically the entire plastics pyramid. If you look at that from peak to PA11 and everything in between, graphene is highly compatible into the thermoplastic. So that is a very important application area, and there's a lot of compatibility with different graphenes there. So another question was about we'll take some different aspects of this. Asking what are the characterization generally for your company for the batch to batch production and what's the batch production volume? Let's just talk about batch to batch consistency, quality control processes, and then overall production capacity. Can you take those?
Yes, I will not steal fully Natasha's thunder. She's the QC manager, so I'll let her handle this. But I will say one of the things that we are so proud of with our graphene is the low batch to batch variability. Many companies, including ourselves at the beginning, struggled with how can you get a consistently synthesized material that won't have these crazy property changes based upon a batch, and you have to just select 20% of your sample. That's something that I can say in full honesty, we do not struggle with at Raymore. But now I'll throw it over to our QC manager to give you more technical details.
Yeah, sure. First, I have to mention that it's 3 years that I'm joining Raymore, but I could say honestly that the production team works really well and they are really expert. They work 10 years to reach to this level. And when we look at the quality of batch to batch, because we do the Raman measurement, which is a really main measurement to understand the number of the layer and the quality of the graphene. We do the Raman in each batches and also the other technique, TEM and ICP. And honestly, I could say that we don't have too much variety in batch to batch. And also, I could mention that we are ISO certified 9001, and we have to look at that. And all the we documented. I saw in the QA that somebody asked that you could provide the document. Yes, because we are ISO certified, and we have a document for all that, and
Ex-
also for the dispersion.
Excellent. We do have quite a few questions to get to, so we'll get to those. So again, please keep them coming. We'll keep answering questions as long as we can. One of the questions came in about testing and how do you test for layer count. And what I would just suggest, I would like to refer everybody to ISO 9651. That's the graphene classification framework. That is a piece of work that was developed over many years within the Graphene Council with over 100 volunteers, and it was published as an official ISO standard a few months ago. And within that, it talks about measurement techniques for different characterization, and it is the standard we use when we test materials. So I'd refer you to ISO 9651 for any testing questions. Then we have another question. You mentioned being able to put at a rather high percentage volume, put your material into a water-based solution or paste. And I was quite curious about that because you have a high carbon content. It's not a lot of oxygen content to make it water soluble.
Right.
And I assume the answer might be that this is your secret sauce. But how do you get your material into a water-based solution or a paste?
Well, once again, I'll let Natasha answer this as well. But we do PVP is used as basically our dispersing agent. And once again, this is a technique that's been developed over many years. I'll let you know it's not sonication. You won't be able to get these levels of loading just with sonication alone. But I'll let Natasha answer.
Sure. We use a different technique for our dispersion because the quality of our graphene is really high. And as you said, that we don't have a functionalized group to be dispersed easily in the water. As Jeffrey said, we use the dispersant like a PVP, but we lower the dispersant to 2%. Even we can go to lower than 1%. And it depends on the viscosity and well, also the content of the graphene. We use a different technique and combining like a sonication, but it's not just the sonication, and also shear rate technique. And as Jeffrey said, that we could with aqueous based slurry, aqueous based dispersion, we can go to the really low viscosity, which is the strength of our dispersion.
Excellent. And
And a very rapid process as well.
I assume the advantage is you avoid the issue with dealing with a dry nano dust, right, with a powder, right? So you have it. So that makes perfect sense. One of the questions here, it says graphene isn't currently listed on the TSCA registry. That would be the EPA
Mm.
Toxic Substances Control Act registry in the United States. So I'm curious how companies are handling this to sell in the United States. And I would like to point out that there are graphene materials that are on the TSCA registry. There were several that were just recently awarded or approved by EPA. And in fact, the Advanced Carbon Council helps member companies navigate the TSCA registry. That's one of the services that we are able to provide to companies who want to have their material registered with EPA. So there are companies on there. The information isn't always easy to find because much of it is kept as business confidential and therefore is not public. So that's maybe why you haven't been able to find it or to see it easily, but there are registered materials. But I would ask you, Jaffor, how do you guys handle US registration?
Right. No, that's actually a very good question. So we basically, whenever we sell to a US based customer, there is an actual, we are on the registry and there is a TSCA form that can be filled out. It can either be done per shipment or it can be declared for the entire year. And it's pretty straightforward form that we send to our customers prior to shipping out our material. They just have to make the declaration that this is not a toxic substance. It would not be used for a toxic application. And then once that is completed and received by the importation agency, usually there's no problem clearing through customs. So that's been our approach, and it's been very effective.
And
Un-
can we add other things, Terence?
sure, sure.
And you know that one of the problem is the PAH, polyaromatic cyclic hydrocarbon, that make it really toxic. The advantage of our graphene is we don't have it. And because of that, the transportation and sending the sample and selling our graphene to the United States, we don't have any issue about that because we
Excellent.
don't have any PAH.
Thank you. So one of the key aspects, especially for using graphene with silicon chemistry with batteries, is the reduction in swelling. Can you just talk a little bit? There's a question about what is the mechanism about the reduction, how does that work, or elaborate why that works that way? And then in terms of cycles, I think in the graph that was displayed, the questions about there were 200 cycles. Often the batteries are tested to much higher cycle life. Can you just talk about the mechanics of the reduction in swelling for silicon in the battery technology, and then about cycle testing and how high you may have tested?
Sure. Actually, I'll take one part. Natasha will take the other, as we've been doing. So first of all, just on a high level. So as I stated with the turbostratic morphology of our graphene, so with the silicon, the graphene actually is able to wrap the silicon. And so this basically creates just a physical barrier. We could talk about the chemistry in a little bit, but this creates just essentially a physical barrier that prevents the expansion. And with that, it then creates this amazing electronic benefit. Now, in terms of the cycles, yeah, I've showed you publicly available information from, like I said, Northwestern University did some proof of principle work with the graphene. But of course, when it comes to real battery applications by our partners, we're talking thousands of cycles that have been tested and have shown to be very effective to increasing the capacity. So yeah, I just showed, like I said, a graduate level results just to show some results that I could share publicly.
Understood.
But that's Tasha.
Yeah, that's really great, Jeff, for your explanation. Just I wanted to add that when we have a silicon anode battery, we have a lithiation and delithiation. And after the, lithiation and delithiation, the silicon is because they need the space to receive the lithium expansion and to remove the lithium from the structure is a contraction. And this expansion and contraction make a cracking on the silicon, and the silicon is fall apart. Therefore, the capacity is decreasing. The things that nowadays is really demanding is wrapping the silicon with something to keep it all the particle together. The best one is the graphene. Why? Because the graphene could wrap it and at the same time could keep the conductivity. With a polymer is effective, but with the graphene is excellent because at the same time wrapping and have a conductivity with the other particle of the silicon. But I don't think so that because it's confidential, but our client using for wrapping and making the network conductive network in the silicon anode battery.
So we do have some questions along that line as to how that happens. How do you actually, because understanding how you're making the turbostratic graphene, I think that's pretty clear and easy to understand, and you showed us how that works. Are you able to speak to how do you actually incorporate the silicon into the graphene or get the graphene wrapped around the silicon particles?
Uh, Honestly, it's confidential, and we couldn't explain it because the client use our graphene for wrapping the silicon. But I can say that the main important section is our dispersion, because if you have a stable dispersion. And with a turbostatic graphene, you could see that mainly you have a double layer, monolayer, and it helps to wrap the graphene really well. This is the advantage of our dispersion compared to the other. And also the other things is the turbostatic structure of the graphene, because it's make it really it's not just a straight, it's not just a turbostatic. We have a crumble and turbostatic morphology that could wrap and adjust and cover the silicon particle.
Yeah, and I would like to point out that there are other companies, at least one other company that is using a similar approach, right? The silicon and graphene combination. And I think it's good that there's more than one company that does this, because it proves that that's a trusted approach and technology to it. It's repeatable, and that there is alternative source of supply, which sometimes for a large customer is a concern that, if there's only one company in the whole world that makes this, that could be an issue. But I think it's a good use case that this is a well-used, proven approach as a battery material. I think that's quite good. Now, you guys are in a unique position because you do make single wall carbon nanotubes and you're making graphene. And in the carbon nanotube world, the vast majority of the volume is going into batteries. And
Right.
so one of the questions is, what are the advantages or the comparison between the graphene you're making for batteries and nanotubes?
Ah, right. Before I get there, I did see
Yeah,
that Muralitharan asked a question that was in the presentation, so maybe it was just missed. She wanted to know, I'm not sure if it's a man or woman, I'm sorry, but they would like to know the lateral size. So the lateral flake size, just so I could bring that
yeah,
point, is 100 to 200 nanometers in answer to that question.
perfect.
Yes. So, okay, yeah. So we we previous in the past we've as many here have known, we used our inductively coupled plasma reactor to produce both single wall nanotubes and graphene. Totally great for batteries. Um, as a smaller company, we have to adjust to what the market is demanding, and we did find that we've had, more demands for our graphene. So we don't produce right now single wall nanotubes that are being used in the batteries applications. The single nanotubes that we're producing are very high purity, I guess chemically, electronically enriched. That's not used in batteries. It's used for different types of applications. So when it comes to when we're thinking about using anodes, cathodes, that's really where our focus right now is the graphene for that application.
Okay. Well, that makes sense.
Yeah.
Um, I just want to read through some of the next questions here. Um,
I can add something in general about the comparison between the
Oh yeah,
using
but yes, right.
single
I didn't
carbon
answer that.
nanotube and graphene. It depends of which kind of benefit you can get it from the conductive additive, because the graphene is a 2D material. And the carbon nanotube is a 1D material,
Mhm.
and it's like a tube, and you could have a connection. But we can, for sure, the combination of the graphene and carbon nanotube has a synergy and is the best one. But the problem with a carbon nanotube is the purification of the carbon nanotube, because usually carbon nanotube has a metal content, and in the battery you have to reduce, especially the iron one. And this is increase the price and carry the more defect on, because you have to do the wet chemistry, a defect on the carbon nanotube. And because of that, nowadays every company goes to use graphene, because the graphene, especially our graphene, because we don't have a metal content and it's a high purity, and you could use it directly in the cathode and anode material.
Excellent. One of the questions from gentleman Jim Morrison, can your graphene be dispersed into engineered polymers? I think we discussed that already, like polyolefins, and the answer would be yes.
Yes.
Can you elaborate on the dispersion and reduced tendency to re-aggregate? So aggregation with graphene is a known problem because the stuff
Yes.
wants to restack and come together. Is there any issue with this aggregation or restacking? And is there a strategy that you have?
If you let me, I can answer that one.
Yeah.
That's a really great question. Because we have a turbostatic one, the turbostatic has an advantage. It means that when the layer is dispersed and is far away each other, the tendency to agglomerate it is less. And because of that, we have a stable dispersion and we don't have agglomeration. And we check the particle size for 1 year and nothing is changing. That's quite stable.
Excellent. So we do have another question asking about market related, asking for case studies and cost analysis and everything else. So what I would just ask is anybody who's interested in understanding some of the commercial aspects, just reach out to the team at Raymore Nanointegris directly, and you can ask your questions and discuss price. We just don't do that in the public forum that we have today. But thank you for the interest in that. And we certainly encourage you to contact them about commercial conditions for the materials. Another question was the comparison between graphite and graphene, composite graphite with silicon. I'm not sure the comparison, or basically ask the question a different way. Which battery materials do you feel like you're most closely competing against?
Yeah, no, we have found that, I mean, there will still be graphite in the silicon lithium ion batteries using silicon anodes. So it will be a composite. I said the anonymous attendee's question. It will be a composite of our graphene and our graphite. It's not meant to be a complete replacement of graphite. We're talking a few percentages that will lead to great benefits. And that's why, I stated that if you're looking at cost modeling, the benefits that you'll see in performance will be worth it. And that's also because you're not going to replace all of the graphite with our graphene unless, yeah, that would just be economically unfeasible.
Excellent.
Yeah.
Well, we still have a few more questions. We will capture these, and I think what we can do is follow up offline because there are quite a few more, and I think we're coming to the end of our time. So with that, I just want to promise everybody we will capture all of the questions. We will follow up with you on that, and I'll work with the team so we can maybe get you a written reply to some of that. But I think this presentation did an excellent job of kind of giving an overview of the production process, the application process, the advantage of using this, and the silicon graphene combination as an anode material is a really well proven technology at this stage. And so I think that's very encouraging. Jefford and Natasha, do you have any last comments before we wrap today's webinar?
Just small. I just wanted to thank everyone for listening. I know it was a very well-attended seminar, exceeding our expectations. So if you have any, further questions about the material or interested in testing, sampling, or purchasing, please feel free to reach out to me with the contact information you could find at the end of my show.
And also, I want to say that thank you so much, Trans, for this opportunity, and hope we could find a really nice collaboration with other company to promote our graphene and also carbon nanotube.
Well, it's our pleasure. We're so happy to have you guys as members, and I want to encourage anybody out there, if you're interested or you're active in this space, whether you're a producer or a user of these materials, to reach out to the Advanced Carbons Council. Now is a great time to join. We just released our newest graphene report with updates on and profiles of companies, applications, market trends, and developments, including pricing information. We also just concluded our most recent survey of the graphene sector. We've been doing these surveys since 2013. So we have, or 2016 rather, so we have 10 years of longitudinal data, and we have a report that will be included with membership as well. So if you have any questions or in general just need information about the graphene or the other engineered carbon sector, that's what we're here for. So with that, I want to say thank you to everybody who attended. Jefford, Natasha, thank you for sharing the information. And we look forward as well to continuing to work with you as valued members of our organization. Thank you to everybody who's listening. And please reach out if you have questions for Raymore and Nano Integris. Thank you so much.
Thank you, Terrence.
Take care.
Good day, everyone.